Good evening. Whoa, it's a huge crowd. This is so nice from here. Thank you all for coming, and thank you to the organizers for inviting me to give this talk. So it's really a pleasure for me to be here today telling you a little bit about what we know about Jupiter. So this is what we will be hearing this night. And in particular, we also be telling you a little bit about a space mission that I'm involved in. I'm part of the science team of the Juno mission that is right now orbiting Jupiter. So you will be hearing about this mission, about the things that we are learning, and also about why we care, why it's important to know more about Jupiter. So the first things that I want to say are just to make sure that we are all on the same page. So I will just say a few things about Jupiter itself. So Jupiter is the biggest planet in our solar system. And you can see there the sizes of all the objects in our solar system. Here is, I don't know if you can see, this is tiny with that screen, but the huge thing is the sun, that is our central star. And then you can see all the other planets down here. So the small ones, tiny ones, are the rocky planets. You see there Mercury, Venus, the Earth, and the Moon, and Mars there. And then we have the giants and the small dwarf planets. So Jupiter here is the king of the solar system. It's really the biggest one, and for that reason has a huge influence in our history as a solar system, right? As part of the solar system. So that's one of the reasons why we want to know more about Jupiter. But the other giants, you see, are not tiny, so they are also relevant as well. So we also care about Saturn, Uranus, Neptune, and even the dwarf planets have their part to play in our own history. Now, a few more things about Jupiter. And I want to mention what is the composition. So how is this planet look like? And if we compare the composition of Jupiter with our own planet, you see that they are very different. We have that Jupiter here is made mostly of hydrogen and helium, and a tiny, tiny percentage of the rest of the periodic table that in astronomy we call metals. So I'm sorry if there is a chemist here, but the rest of the periodic table for us is just a tiny, tiny, tiny thing. So Jupiter has a really small percentage of all of that. If you look at the Earth, you see that it has iron, oxygen, silicon, magnesium. It's very different from Jupiter. So this is the very first thing that we can learn, that is completely different. It's another thing. And it's also interesting that in Jupiter we cannot go and, stand. There is no surface. It's completely made mostly of these elements, so that's why we call it a gas giant. It's not really that it's a gas like a cloud you cannot go through, because the pressures and temperatures are very, very high in the interior of the planet. So you could say that we can think of it as something like, a gas giant, something that you go through, but in reality it's more like a fluid, a gigantic fluid that we have there in our solar system. If we compare now Jupiter with our sun, then we will see that actually they look pretty similar. The sun also is mostly made of hydrogen and helium and a tiny, tiny percentage of the rest of the periodic table. So Jupiter is more similar to a star, to our sun, than it is to a rocky planet. So it's a completely different beast. And that's why we separate them. We have a name for these planets, gas giants, Saturn and Jupiter. Uranus and Neptune, they are a topic for another talk, because they are also something completely different. So we have only those two planets, those two giants in our solar system. Of course, those are not the only gas giants that we know. There are also planets around other stars, and many of those are also gas giants. So we can study the ones in our solar system to also learn a little bit more about those ones that are so far away. Now, This is like a great, great time to study giant planets. Not only in our solar system, but as I said, those ones around other stars. And the reason for that is because we had two great missions that went around the giants in our solar system very recently. We had the Cassini mission that went around Saturn and was orbiting the planet for many, many years, and really gave us amazing information to understand the interior of Saturn, the atmosphere, the satellites, the rings. So we are learning a lot about Saturn still with data that we are analyzing from the Cassini mission. And as I mentioned before, we have now data for Jupiter as well, thanks to this mission that is called the Juno mission. So I will be mentioning a few more things about this mission later on. Right now, I will just tell you that this has been orbiting Jupiter since 2016, and it will be there until 2025. So we still have a few more years for this mission to keep learning about Jupiter and about the Jupiter system. Now, I also mentioned that this is a great time for studying giant planets because we have information for exoplanets. And we also had a few missions, but that not really went to exoplanets. They were just satellites that were orbiting the Earth, and that helped us to know that there are many planets out there. Here, I'm going to mention a few of those missions. So the Corot was an ESA mission. It's not there anymore. The Kepler mission, that was a NASA mission, and this one that is TESS, that is also NASA. All these three were really helping us to know, to discover many exoplanets. They were, as I said, satellites that were orbiting the Earth, were there for many years, and thanks to them, we discovered thousands of exoplanets, thousands of planets around other stars. So here is a nice movie where you can think that the planets that we know are only around the stars that are very close to our sun. So really in the solar neighborhood, because it's very difficult to find those worlds. But there are so many. We look at a tiny piece of the sky and we found lots of planets. Another region and lots of planets. They are really, really abundant. So you can think that in most of the stars that you look at night, they might have planets around them, which is really amazing, something really cool to know, and that we've only knew for 30 years. So it's something that we can say, right? It's the first time in human history that we know this, so it's very exciting. And then what we can do is to put together all that information of the planets in the solar system for which we can go and we can make measurements, and also get together all this information of the 5,000 exoplanets that we know exist out there and try to understand better how giant planets work, how they were formed, how are their interiors, their atmospheres, how they influence also the smaller bodies in a planetary system. Now, why do we want to study them at all? Why do we care? Why do we send those missions to Jupiter, to Saturn? Why we want to know more about exoplanets? Well, there are many reasons. I will tell you a few of them. And sorry, but I wanted the previous slide. OK, this one here. So if we think of our solar system, at the very first stages of the formation, we had that the sun was first formed, and then from the remaining material of the formation of the sun, there was a disk around it. This disk had dust and gas, and from that disk, the entire solar system was born. So this is kind of what the animation is showing. The first objects that were forming that disk were the giant planets, which, when I learned about this, it's counterintuitive because they are the biggest ones. So in my head, I thought probably they should take longer to form. But actually, they are the first ones that form in a planetary system. And that's because they have all this gas that is the first thing that disappears. In a few years, in a few millions of years, it's gone from the disk. While all the dust and the remaining rocks, they remain there for millions and millions and millions and millions of years. So these ones, Jupiter, Saturn, were the first planets that formed in our solar system. And that's why they have in their interiors and atmosphere so valuable information to understand the very first stages of the formation of our solar system. Also, giant planets are not like the Earth that had a differentiation, that went through lots of changes. Giant planets are more or less primordial. They, of course, evolve, but that gas is the primitive gas that they acquired at the very first millions of years of the formation of our solar system. So that's one of the reasons why we want to know more about them. It's not the only one, though. Another very important reason is that they are natural laboratories, we say. And the thing is that they have in their interiors particular conditions that are in no other body. They have, for example, in the very center of Jupiter, we have temperatures of 10,000 degrees, centigrade or Kelvin. At that stage, it doesn't matter, 10,000 degrees. And the pressures are really high, are of the order of 10 million times the pressure that we have here right now. So those are very peculiar, conditions that we don't have in other bodies. And then this pushes us to study, okay, what will happen with rocks at those pressures and temperatures? What will happen with mixtures of ices or with hydrogen or helium? So they really push us to study the elemental things of some elements. And that's why we say that they are natural laboratories. And I will come back to this during the talk. They also highly influence the dynamics, the movements of all the other bodies. So we know that they didn't form in the place where we see them today. They formed somewhere else. Actually, we don't know really where they were formed, and there is a huge discussion these days in the community to where was Jupiter and Saturn and these planets formed. But then what happens is that they form and they move around. They go closer to the sun or they move farther out. We call that planetary migration. And this is quite a common stage of the formation of a planetary system. So imagine that you have this gigantic Jupiter and Saturn pair moving around. Everything on their path is going to be, moved as well, scattered away. So that's why we really want to know what happened with them, because they had a huge influence on what happened to the rest of the solar system. For example, our planet was formed in a very dry place. Dry because it was very close to the sun that was super hot at the time. And then one of the big questions that we had for a long time was how is that water arrived to our planet? It was not in an ice form or easy to be there at the time. So then we think that Jupiter was moving around and was sending to the Earth comets and asteroids that had a lot of water. So we believe that we are all here and we have our planet nice and habitable, also thanks to Jupiter. And that's another reason to why we want to know more about this planet and about what happened during its formation and evolution. So I hope I convince you all here that it's very important to know more about these planets because they actually tell us a little bit more to learn about our own history. And that's why we want to know more about them. Now, which is our history observing Jupiter? Of course, we knew these things for a long time, so we've been trying to learn more about these planets for a long time. And here you see the very first person that was actually observing it with a telescope, that is Galileo. So our history with Jupiter started a long time ago. And here is a nice letter that Galileo drew showing his results. So you can see here in the drawings, this is Jupiter, and you see there the 4 main satellites, what we call the Galilean satellites these days, where he was observing that they were actually moving around Jupiter, which was a revolutionary thought at the moment. So he was really the very first person that was looking at Jupiter like that with a telescope, like going beyond. But of course, we all can see Jupiter with the naked eye, right? So actually, our story with Jupiter starts way, way, way long back. Now, after Galileo, we sent many missions to the planet. So the Juno mission is not the first one. We had the Pioneer missions, the Voyagers, the Galileo, and this one was actually quite important because it was the first one that did a dive into the atmosphere and made in situ measurements. So we still today are using very valuable information from the Galileo mission. Then we had these two that actually were not, the target was not Jupiter. So Cassini went to Saturn and New Horizons went to Pluto. But on their way there, they also did a flyby around Jupiter. And we have the Juno mission today. So this is more or less our history with this planet and all the data that we've been collecting during the years. Now, you might wonder, OK, why do you keep studying it? After seeing it with the naked eye, with a tiny telescope, we can see Jupiter. We have all those missions that went there. You have tons of data, so you know everything about that planet. But that is not true. There are many, many questions that we still don't know about Jupiter. And some of the ones that I will be talking about today, and that really drive me crazy to know, is what is Jupiter made of? So I showed at the beginning a very nice drawing with the composition. Well, that part, that was the metals, so the rest of the periodic table, we don't know that very well. We don't know exactly the amount of those elements in the interior of the planet. We don't know the percentage of each one of them. We don't know the amount of water in the interior, the amount of rock-forming material in the interior. And that is very important to understand where the planet was formed. Because in this disk that I mentioned at the beginning, we had that very close to the star, the temperatures were high, and then we had more rocks. The ices were more in a gas form there. And then when we went farther out, things were cold, and only the ices were there. So if we know the amount of rock-forming versus ice-forming material in the interior of Jupiter, we will know more about where the planet was formed. And that's one of the reasons why we want to know this so badly. The other thing that we want to know is how is the internal structure of Jupiter. So how is that all these materials are distributed in the interior of the planet? And that is something very difficult to know, because it's not that we can go to the core of Jupiter and actually see what happens in the way there. So these are really the questions that I want to know and that I will be telling you a little bit more about. But it's also why we sent the Juno mission out there, because we still had those questions, and they were really fundamental to understand the origin of Jupiter and the solar system. Now, let me tell you a few things about the mission. So I mentioned that it's a NASA mission. Here is a nice schematic figure of the spacecraft with a person here. And Juno is doing a lot of science. I will just tell you a little bit of this today, but there is a whole lot of things that we are doing with this data. So you see here, this instrument is called a magnetometer. It's measuring the magnetic field. The magnetic field of Jupiter is the biggest in the solar system, so it's really, really huge. And we still don't know things like, for example, where it originates. Then we have lots of other instruments inside here. This is actually a titanium vault, because the spacecraft has a very suicidal orbit, let's put it that way. I will show you a little bit more later. So then we needed to protect the instruments from all the radiation. So they are inside there. And then you see these huge solar panels. So Juno is actually the first NASA mission that went to the outer solar system with solar panels, which also required a huge effort from the engineer team to make sure that the spacecraft is looking at the sun all the time in all the orbits that it's going to have during all these years. Now, I found that when I tell people that I work with a space mission, everyone wants to know how is it? Like, how is the experience of working with a space mission? How is the people? How are the meetings? So I will tell you a few things about that. Particularly, my story with Juno started in 2016. So the year that the mission arrived to Jupiter, I started working with the team, which was a perfect timing from my side. I have to say that preparing these missions takes super long times. So, for example, the Juno mission they started to think about sending this mission to Jupiter in the 2000. I was just starting my studies in astronomy at the time. So it really takes a long time to plan one of these missions. And what you are seeing there is all the team of the Juno mission. We all got together when the mission was going to arrive to Jupiter. So you see on this side all the scientists, on this side the engineers. Here is the management team. I'm like standing like right there. You see that the spacecraft is on the original size, so we were just having a lot of fun. We all got together, we made this movie, we had a big party. Actually, I even have pictures of that. We were very excited and made these tattoos. It was not real, but we were like having a great time. It was really awesome to be with the whole team. It's also, that's me with the press part, because the press was also there. It was all like it's NASA. They know how to do these things. It was a huge party. Then, of course, we were all on our room. Like, the tension was there. We didn't know if the mission was going to arrive safe or not. And let me tell you, it was a real tension. Like, space is very difficult. Making sure that someone leaves the Earth and arrives to someplace so far away the day that you want it to arrive, because it arrived on the 4th of July. They planned this perfectly. So it's like almost a miracle if I think about it. Like, the engineers did an amazing job, because this is very, very difficult to achieve. So we were there like, okay, is this going to arrive safely or not? They didn't tell us anything. And then, of course, we knew it arrived safely. We were all celebrating. So it was really, really an amazing experience, I have to say, having been part of that. And of course, after that, we meet every 6 months. We have fights with each other. It's like, this data is not what you say, and so on. So, but this is in total a really great experience to be part of this mission. And of course, the data that we are getting is really mind-blowing to learn more about Jupiter. Now, I told you that it had a little orbit that was a bit crazy. So this is the orbit that the spacecraft has. It takes 2 months for the spacecraft to go to do all of this. And Jupiter has around it like a belt of radiation. So the spacecraft is passing through that belt at each orbit. And each orbit is of 2 months. So it's passing through that belt of radiation very often. And that's why we had to put the instruments in this titanium vault. This orbit is on purpose, like this, because many things. So one of the things is that we wanted to know more about the poles. So far, before Juno, we had no images of the pole of Jupiter. There is no way of seeing the pole from the Earth because of the geometry. So, and all the other spacecraft only went around the equator. So we really wanted to know more about the pole. But also, because if you see, this is kind of shifting. So also the idea is to have a complete map all around the planet when the mission is done. So then we actually have information of the entire planet. And another thing is that if you go really, really, really close, you get better gravity data. That is what I care about, to learn more about the interior. So I will tell you more about that. This is just a nice animation. I thought it was pretty cool, that is showing how the spacecraft looks at Jupiter. So I think it's just fun. But you see that when it's very close, it's actually very close to Jupiter. So it's passing 4,000 kilometers above the clouds. So super, super, super close. Another thing that not everyone knows is that there are some passengers on board of the spacecraft, and are those tiny Lego figures. So that was not the original plan. They wanted to have real bones of Galileo going on the spacecraft, which of course didn't happen. So then they decided to replace them with some nice Lego figures. I know they are not the same, but they are pretty cool. Kids love them. So we have on board of the spacecraft, here is Mr. Galileo, and then we have here Jupiter itself and his wife, Juno. So they are there, and we're a cute thing. Kids love it, and we love it too. And now let me show you a few of the amazing images that we have. So this is a time lapse made with the camera that is called the Juno Cam. And these are real photos of Jupiter. They are a little bit touched. The contrast, the colors are enhanced. But it's really what you could do with Photoshop. So I think it's really amazing that we have such beautiful images of Jupiter. And on the first plan of the mission, there was no camera. So they sent the proposal to NASA, and there was no camera there. I was not in that part of the mission. So I'm really glad that they fixed that, and they put this camera, because come on, are you going to send a spacecraft all the way to Jupiter without a GoPro or something? So it's amazing that they did, and that gave us the opportunity to have these beautiful images. So here are just some of my favorites. You can go to the website and check them on your own. You can download the raw images even and play around with them. So you see the beautiful colors. Even the clouds are there. So it's really amazing. This one is like an art, I would say. It's just really beautiful. Here you see all this blue. Like, we've never seen this blue in Jupiter before. So I think this is one of my very favorites. You see all the turbulence. It's just incredible. Here you can see all the bands, the famous bands and belts of Jupiter, really, really nicely. This one is kind of like the blue, but purple. Like, we have all these colors there, which is really, really great. We've never seen them like this. And this one I also like, because it's not the typical picture that we see of Jupiter with the bands and belts. This is more taken from this direction, looking at the pole. So then that's why you see kind of like a different Jupiter than the one we were used to. Now, I told you I was going to mention a few things about how we do the science, and let me stop this first. So imagine that Jupiter is a perfect sphere. All the matter is distributed homogeneously there. If that would be the case, we can calculate which is the orbit that the spacecraft is going to have around it. And this orbit looks more or less like the blue thing that you see here. So relatively, we can calculate that. Now, in reality, that is not what happens, of course. Jupiter is not perfect, and there are some inhomogeneities. Some matter is distributed unevenly in the planet. And that is really what we want to know. We want to know how is the density distributed in the interior, how is all this matter distributed, where the different elements accommodate. So luckily for us, Jupiter is not perfect, and then the spacecraft has not that perfect orbit, but instead has an orbit that looks more or less like the orange thing that will appear like now. So then it's more like this thing here. And we are in contact with the spacecraft all the time, so we can map the real trajectory that it has. And all those deviations from the perfect trajectory are telling us something about the gravity field of the planet. So where this matter is accommodated, how are those inhomogeneities that are creating that the spacecraft moves a little bit from this perfect trajectory. So this is really the data that we use to try to map the interior of the planet. And imagine that this is something very difficult to do, right? In the Earth, even, we cannot do a hole and go to the center of the Earth. We study the internal structure using seismology, using earthquakes. We cannot use that in Jupiter. First of all, it doesn't have a surface. So even if we wanted to send seismologists here, it wouldn't be possible. So we have to think on other ways of studying the interior structure of the planet. And this is the way that we are doing it. Now, we want to study lots of things. So here is just a nice cartoon representing the different. I will show you another schematic figure talking more about this. But we wanted to know the interior of the planet, the atmosphere, how these connect, and in general, what the planet looks like. Not the part that we can see, but the rest. So it was more difficult to do. Using this technique, all this gravity data, one of the things that we could learn for the first time is the depth of the Great Red Spot. So we've seen that image of the Great Red Spot. We can even see it with a small telescope. You see the spot, so it's really amazing. But of course, when we see in astronomy, we see in 2 dimensions. We don't have the depth of things. And that's usually the hardest thing to get and where we have to be creative. So we were using this mapping the inhomogeneities of the planet to actually came up with the depth of the Great Red Spot. And we found that it's of 500 kilometers, approximately, which is let me tell you a tiny, tiny, tiny thing for the entire radius of the planet, and I will put you this in perspective shortly. So here is one of the real images, let's say, that we use. So we use this gravity information, but we also have images at different wavelengths, which represent, let's say, we see a different depth in the planet, and then we can map those depths. So here you see the great red spot, and here you see it very dark as well, and you see that it's getting lighter and lighter and lighter and lighter until we don't see it anymore. So then we knew that it was gone, and we combined the real data that we have with the gravity data and found the same results. So this is really something very nice that we found. Another of the big results that we got was about what we call the differential rotation. So when we see Jupiter, it looks more or less like this. This is actually a movie made by the Cassini mission, where you see the bands and belts of Jupiter that they actually rotate in different directions, at different velocities. So we knew this for a long time, and we called this the differential rotation of the planet, which means that it's not that the entire planet rotates like a block, but it has this thing. And again, what we didn't know is how deep those winds extend into the planet. And we used this same technique, the same one that we used to understand the depth of the great red spot, to actually map this for the first time. And what we found is that Jupiter has, when we think of its rotation, a structure that looks more or less like this. So this is a very nice animation made to explain this. So you see these belts that have a depth of approximately 3,000 kilometers. This is more or less 4% of the radius of the planet. So it's just tiny, tiny, tiny thing. And imagine, this is 3,000 kilometers. The great red spot was 500. So it's not even the depth of the entire belt, right? It's a huge storm, but in terms of what Jupiter is, it's actually not so deep. And then what you see down there is the rest of the planet. It really rotates like a block, like a rigid body, we say. And this is, of course, very important for us to understand the internal structure of the planet. We need to know how the planet rotates to actually make our models for the deep interior. Now, let me tell you, awesome, see, I need to give talks here more often. Thank you so much. So we use all this data to know more about the internal structure of the planet. And now this is, I'm going to show you this diagram that I made. So it's not as nice as the one that NASA made before with the movie, but this is a very recent results also, so I hope you appreciate it. So this actually shows the interior of the planet, or how we believe the interior of the planet is, that explains better the data that we have today. So Jupiter is basically made of all these different layers. This one here is the outer layer, is dominated by hydrogen and helium. Hydrogen is in molecular form, so it's a gas, an actual gas there. And of course, we have a tiny, tiny percentage of all the rest. Then, if we look at this layer and we try to think on the previous things that I mentioned, where do these belts extend if we look at it this way? So they extend more or less there. So this dashed line represents the depth of all the belts and zones that we see in Jupiter. So they are very superficial if we think of the entire interior of the planet. And the great red spot there, I cannot even put it in this figure because it's really tiny if we compare. So it's an amazing storm. It's great to study the dynamics and the weather of the planet. But in terms of the internal structure, it's really a tiny, tiny thing. If we go even deeper, then we have this region that we call the helium rain. So what happens is that when we are out here, then hydrogen and helium are very well mixed. They are like when you put milk in your coffee. Everything mixed, no problem there. Now, at some point, there are some pressures and temperatures where they just don't want to be together anymore, and they separate like water and oil. And then they create these distinctive layers because they just separate like this. And helium forms droplets. These droplets are very heavy, so then they rain down towards the center of the planet. And then we have here this region is depleted in helium, and this one here has an overabundance of helium. Now, this thing, let me tell you, is very, we were thinking that this might be the case since the 70s, but this was all theoretical. We only got laboratory confirmation of this phase transition last year. So this is really, really, really something that we thought was the case for a long time, but we only got confirmation now. So it's really exciting. Now, if we go even deeper, then in this region here, I told you that we have an overabundance of helium. When something happens to hydrogen as well, hydrogen also has a phase transition deep down there. And it's not a nice molecular gas anymore. It becomes what we call a metallic fluid. So this phase transition of hydrogen only happens in the interiors of Jupiter and Saturn. It doesn't happen in interiors of stars. It doesn't happen on the Earth or the other, or Uranus and Neptune even. So this is really something that we learned thanks to studying the interiors of these planets. We didn't even know that that phase transition happened for hydrogen before that. So that is what I was telling you at the beginning, that they are really natural laboratories. We don't even know the applications that knowing this phase transition might have in the future. So this is really the beauty, in a sense, of doing this fundamental research. Then we go even deeper. We have two more to go. This one here is what we call the dilute core. So actually, if we go to the very, very center here, we have the core that is made of more pure rock and ice-forming material. So no hydrogen and helium there. And then all that material dilutes slowly into this envelope and creates this other layer that we call the dilute core. All this is really, really new. We didn't know this. For a long time, we didn't even know if Jupiter had a core or not. It was not, we couldn't know this with the data that we had before Juno. So thanks to this very exquisite gravity data that we got with this mission, we could really figure all these things out. So if you ask me in a summary, what can we say? Which are the things that we learned with Juno these last years? Then I think this summarizes this very nicely, because it tells you what we learned about the Great Red Spot, about the differential rotation of the planet, and about the internal structure. Of course, we learned many other things about atmospheres. We could even measure lightning in the planet. We are understanding the weather. But that is really a topic for another talk. So today, I wanted to summarize what we know about the internal structure, and this is what we believe it's inside Jupiter today. So with that, I'm going to end this talk, and I hope that you have many questions for me. Thank you.
Junk